All right. Well, thanks for coming on your last day of before break. So questions? Everybody good on PA5? So we'll start presentations Monday morning. And basically, whoever from your group has a laptop that your code runs on, bring it up. We can connect to VGA, we can connect to HDMI. If you have a Mac, you're going to want some kind of converter.
I do have I think this is Thunderbolt, is what at least my MacBook takes, so I have a converter to HDMI.
Okay, perfect, cool. So yeah, I'll have each group come up and basically just show us your code. Talk to us about the project itself, what was involved in making this work, how you worked as a group, how you split things up among different people. If you used Git to share your code, you can talk about that. If you decided not to use Git, right? You sort of tell us about the group aspect of it itself. And then demo your code, show us making a few reservations, writing a reservation for someone who already exists, show us that it gets replaced in the file. And then any bells and whistles that you put in. If you put in checks so that you can't, fly to the same city you're leaving from or can't go back in time, you can demonstrate those. And then just kind of run us through your code, anything in particular that you want to point out. You don't have to take us line through your whole script, but anything that is noteworthy in there to you, you can talk about. And typically it's about 5 minutes per group. But just to kind of give us an idea what you did. So we'll start those Monday morning, and depending on how many people show up, that may not take too long. All right, everybody good on the SLP? I sent your posters in this morning at 6 o'clock to get printed, and they're already in my mailbox. They're like super fast at production printing. So I've got those. And so that'll be on Tuesday, 3 o'clock. All right, well, we're playing with processes. So we talked about execl, or exec-v, right? And exec-v was a way to basically start running another piece of code, so we could what did I call it? Go zero. Go zero. So we can call exec-v and give it an executable file, right? And it basically loads the code from that file into its own memory, and it becomes that process, right? It becomes a process that's executing that binary code. So that's exec-v. Whether we do that or we do system, or we do a fork and we run this in another process, right? One of the problems is the output of that command is sent to standard out, right? And we can redirect it with a greater than sign into a file and then open the file, but that's not terribly convenient. So let's look at what we can do with pipes. So we're going to look at a command called popen. It's a function, chapter 3. And popen basically takes a command and then a type. So I don't know if we've talked about fopen in formal detail, but fopen is how we can open a file. Did we discuss this?
We discussed it in Intro to C.
Okay, but not in here. So you can fopen a file, and then you can do fgets from that file. Instead of saying standard in, you put in the file object that's returned by fopen, and you call fclose. To close it, you can do fprintf to write into the file, and so on and so forth. Okay, so there's another version of these things called popen, and so we can do popen and we can do pclose, and they take the same set of arguments. Popen takes file name followed by a type, which is like R or W for read or write. But what popen does is it creates a new process and starts that process executing whatever command you passed it as the first argument. So it's another way to create a new process that starts executing a command, but the output of that command can be accessed from this file object that you get from popen. Or you can specify standard in to that command using that file object. So you can open this for reading or writing. And so we can do things like this. So let's do popen on bin date, and let's open it for reading. I'm going to take the return from that. I'm just going to call that FP, my usual file pointer. And I'm going to say, well, fgets FP, fgets from FP is not null. I'm just going to close this at the end. So buffer is just a character array. So I'm going to open the date command, and then I'm going to read from that FP, that file pointer, using fgets. And it's our standard fgets call. Instead of saying read from standard in for the third argument, I'm reading from FP. And as long as it doesn't return null, I'll just go ahead and print out the thing that that fgets gave us. So if I run this, it tells me fgets returned, and that's what it returned. It returned the output of the date command. So if I do popen with /bin/ls, then fgets gets called a bunch of times, and each time it returns the next line of output generated by the ls command. So now I have a very controlled way to look at the contents of a directory from inside a C program. I can just say popen ls. I can put the path into the directory if I want. And each time I call fgets on that file pointer, I get a new line from ls, which is another file in this directory. So we can execute commands in other processes, but capture the output and do something useful with it if we want. And I can do something like /bin/ls star.c, right? And it shows me my .c files. I can do ls-l star.c, and there's my long listing. So all the stuff you can do from the bash command line you can do in a popen or in a call to system, including things like switches and things like wildcards. Right? And we can do a lot of stuff from bash. We know we can take a command, we can pipe it into another command. We've got awk and sed, right? But if you really, really need fine-grained control over the output, right, you can do something like this, and you've got a string in C with a line of output, and you can, process that a million different ways, depending on what you're trying to do. All right, so we can also open something for writing. So let's just pick on our binary calculator program. So you remember what BC is, right? BC, you can type expressions into and it evaluates those expressions for you. So let's make a popen on the BC command. So it's user bin BC, and let's open it for writing. And let's do fprintf. And let's print in the string 2 + 2 with a new line. So we'll create a pipe to run the BC command. We'll print 2 + 2, and then we'll close the connection to that pipe. And now if I run P1, it gives me a 4. Now that 4 is just being displayed on standard out. Right, I don't have access to it because I opened the pipe for writing. But now I can sort of send it whatever I want. So here's a more general purpose version of this. So it'll ask me for an equation. It'll use fgets to let me type in up to 120 characters of arithmetic expression. I'll open the BC with the popen, and then whatever I typed in with my fgets, I'll just print that out to fp, and then I'll close fp. I can't do that. Do it as a %s. And I know buffer will have a new line at the end, so I don't have to put a separate new line in here. So I can say enter an equation, and I can say 234 times 9, and it does my calculation for me. So let's throw out a get card here to pause this program before we close the pipe. So I type in 2 + 3. It printed that out with an fprintf, but we haven't gotten any output yet. This is going to be a lot of output. Let me throw this in the background and just do a PS. Alright, so bash is my original bash program. P1 is the program that I just started running, so that's process 904H. That created a new process 9049, which is SH. That's the Bourne shell. It's a different shell. It's like bash, but it's a default shell, and it's a shell that's used when you call popen. And that shell 9049 executed the command BC, which is process 9050. So when you do a popen, it creates a new process that runs the shell sh, and that shell sh executes your command that you asked, BC, date, whatever. Right? This is why you can do things like wildcards and switches and such, because this command is being executed underneath the Bourne shell. And then once I hit enter in P1, which will just get me past my get car, it'll go ahead and close the pipe, which causes my BC command to actually receive that input. 2 plus 3, it prints out 5, and then it exits. And now if I do my PS again, I'm just back to my bash shell and my PS command. But again, something to notice in here was that at this point, I had printed 2 plus 3 into this file pointer, but BC did not see that yet, right? It's buffered output. Even though this has a new line at the end, and I can throw an extra new line down here. I can throw a few of them in. Right, it sent that out, I put the new line, but that still doesn't actually get it to the process on the other end of this pipe. It didn't actually go through until I closed the connection. So here again, we can use a flush. So if we do F-flush FP, that'll actually force it to go out to whatever's on the other end of that pipe. So now 2 plus 3, we get our 5 back before I actually close the connection. But if I do PS, I've still got BC running underneath shell, underneath P1, underneath bash. So let's open a bash shell with P open, and let's get a command, and let's write that out. And let's make a lazy infinite loop. So let's just read a command from standard in. Let's write that out to our pipe, which has opened up a bash shell. So enter a command pwd, enter a command who, enter a command ls. All right. So now I'm like running a bash shell from inside a C program. And we can do all sorts of things. So this is pretty powerful, right? We can sort of tap into the whole power of Unix and all the commands available in Unix and so on and so forth from inside a C program. And it's just this P open. So that's pretty cool.
What's the difference between F open and P open?
F open is for a file.
Okay, so only for files.
Yeah, so if I do F open, right, like that, and then F close. Right, so all that stuff is getting written into a file, like that. And I'm not closing it correctly because I'm Control-C'ing out of the loop, but since I'm F-flushing, it's actually going into the file while we're doing this. Now, if we don't do that F-flush, right, nothing's gotten written into that file yet. Even though I clearly did fprintf 3 times with 3 lines of text, it's kind of in this holding area, right? Because writing to a file is expensive, right? It's sitting on a spinning disk. It's probably 5,400 RPM because it's a laptop. So to write something to the disk, you have to wait till the disk physically spins around so that the area you want to write to is underneath the read-write head. It takes you a 5,000th of a second. That's an eternity with a 3 gigahertz processor, right? So it doesn't write to the disk every single time that you say write. It buffers it up. When you do F-flush, that forces it to actually get written out. So, and this is kind of what happens when you have a flash drive and you write stuff to it and then you don't bother to eject it, and you just pull it out, and then your file is corrupted, right? Or maybe your whole directory is corrupted. When you eject a flash drive, what it's doing is it's saying, okay, all the stuff that got buffered up to write, go ahead and write it out. It forces all those buffers to get pushed out and cleared. And right now, you know, if I just kill my program with a Control-C, there's nothing in my file. Now, if I'd written 1,000,000 lines of text, some of those would have gotten written, but some of them wouldn't have, right? Because once that buffer gets filled up, it'll dump it out. So I'd have most of what I wrote, but the trailing parts wouldn't be. Well, if that's not a file called if that's actually like a file that contains information about other files like the directory structure, and that gets corrupted, then your whole file system is munged. And you try to read your flash drive and it says, you know, there's a problem. Maybe you can restore it, maybe you can't. So flushing is nice, but it costs you efficiency, but not a big deal for us.
So if you wrote that for more code, you just F-flush in the very, very end?
Yeah, so you F-flush any time that you want to force the output to actually go.
So you just do it once at the very end?
Yeah, you can do that. Or if you close it, that automatically does an F-flush. So let's try this actually. I've never tried this. Let's just print 10,000 important messages to our file. And then let's wait for the person to hit enter. So we'll print out 10,000 important messages. Alright, and if I close that out, then, right, that's got my 10,000 messages. So if I run this, and I don't close it out, then I've got 9,910 plus a little bit more important messages. Right, and if I Control-C that, then it wrote most of it, right, but not all of it. So that's classic file corruption. All right, so what have we got? We've got system, which just executes a command, and it executes as a separate process but we have no access to the input or output streams. We've got fork and exec, which kind of do the same thing as system. System is a bundled up way to do that. But this creates a totally independent process that starts running in parallel with our main process, but we still have no access to input or output streams. We have popen, which will run a command in a separate process and let us either write to standard in or read from standard out. So it gives us half of the access to it. But if we want to be able to write to and read from a process, we need to do something more. For example, maybe I want to run the BC program as a way to do arithmetic. I want to be able to send it an expression and then read back the results of that expression. Right? So I can do large arithmetic using BC. And so we need something more nuanced. So we need two more commands. We need the command pipe, and we need dupe2. And I believe these are both chapter 2 functions, or chapter 8. So there's pipe, which creates a pipe, and dupe2, which duplicates a file descriptor. Yeah, I'm not going to go there. I think the best way to do this without getting needlessly complex. Alright, bear with me a second, I'm going to hack up some code. Let's just go for BC. Alright. We need two more things. We need read and write. So read and write are chapter 2 functions. They're low-level system calls. They're the things that printf and getChar and fgets and gets and everything else are built on top of. Read is used to read from a file descriptor, which is simpler than a file pointer. and write is used to write into a file descriptor. So file descriptors are things, they're integers. And we always have 3 file descriptors available. 0 is basically standard in, 1 is basically standard out, and 2 is standard error. And when you do that 2 greater than dev null, that 2 is saying standard error gets sent to dev null. So that's a file descriptor. So 0 is input, 1 is output. We're not going to worry about standard error. So we read from 0, we write to 1. So we can use this read function. The first argument is the file descriptor, so 0 if we want to read from standard in. The next argument is a character array, and the third argument is how big that character array is. So it's kind of like fgets, but it's much lower level. And we can use this not just to read characters, but to read binary information from a file. And the corresponding argument for output is write, and the same arguments, file descriptor, pointer to character array, and the number of bytes that you want to write. And these get paired up with open instead of fopen. So open is a low-level file open, and we basically put in the path to the file we want to open, and then some flags that say are we open for reading or writing or both, and so on. So read, write, go with open and close. Alright, so we're going to use this pipe function, and pipe is used to create 2 file descriptors that are connected through a pipe. So we pass it an array of 2 integers, it creates a pipe, and it connects each end of the pipe to one of the elements of this 2-element array. And so element 0 is the read end, element 1 is the write end. So what's this look like? Make an array of 2 integers. Pass that to the pipe function. What you end up with is a pipe. This is ends bracket 0. This is ends bracket 1. Whatever you write into here, you can read from there. So it's unidirectional. Things only go in one direction through this pipe. And whatever gets written into the file descriptor that's been set in element 1 of this array can be read from the file descriptor that's been set in element 0 of this array. Okay, why do you want to do this? Because you're going to create this pipe, and then you're going to say fork. And you're going to get a new process that's an almost exact clone of the original process. It's going to have the same array called ends. And now you have a second process with the same thing. And whatever you write in here comes out here. But this and this are exactly the same. This is really just one big pipe. So if this new process writes something into here, the parent process can read it from there. So this sets up communication between a process and its child. So you create a pipe, and then you fork to make a clone, and the child process can write into this end of the pipe, and the parent can read it from that end. Or vice versa. the parent could write into here and the child could read from there. So that's our basic way to set up communication. That's basically what a P-open does for you. Bless you. But P-open only makes one of these pipes, so what we're going to do is we're going to make a pair of pipes. We're going to have one pipe to let the child send information to the parent, and another pipe to let the parent send information to the child. And so now we've got a setup where we have a parent and a child, and we can visualize it like this. Right, and we got two-way communication. So we're going to call this write pipe. And we're going to write into element 1 and read from element 0. And we're going to call this read pipe. And we're going to write into element 1 and read from element 0. So this is the parent, that's the child. Probably in the end, the hardest part of doing this kind of programming is keeping track of who's doing what. When we say write pipe, are we talking about the parent writing or the child writing? And inevitably, when you get tripped up with this and you end up deleting everything in a mad fit of rage and starting over again, it's because you forgot who's doing what, right? Or it didn't get written down or something. This is where comments really help you. So I'm thinking of these from the parent's perspective. It's a write pipe because the parent is writing into this. It's a read pipe because the parent is reading from this. So let's just play with this. Let's not worry about processes yet. So I'm going to make a pair of endpoints for my read pipes and for my write pipes. I'm going to get rid of those S's. All right, so I'm going to put a message saying that I'm the child, and let's read from, so the child is going to read from write pipe bracket 0. And let's just read one character. Okay, otherwise, if fork does not return a 0, then we're the parent. We got the process ID of the child. Let's go ahead and write into write pipe bracket 1. And we'll just write an X. I've never tried this. Let's see what it does. So we create our pair of pipes up top. If we're the child, we're just going to read from the write pipe bracket 0, and we'll print out the character that we read. If we're the parent, we'll go ahead and we'll write into that pipe. Let's see what it does. What's the worst that can happen? Hey, it actually works. So the parent announced itself, the child announced itself, the child read an X. So let's send some message back from the child. So the child is going to write into read pipe bracket 1. So write read pipe bracket 1. And let's just say haha. We'll put a new line on the end. I'm going to say let's send haha new line, and we'll write 5 bytes. So that will write all of that out. And then let's read from, so the parent reads from read pipe bracket 0. And let's read 5 bytes. Let's do this really low level. So let's just write out haha. Now the parent, after it writes an X, let's go ahead and read 4 characters from the pipe, and we'll just print out those 4 characters as 4%Cs and see if it gets back haha. Right. Okay, it's not a terribly exciting output display, but it's really pretty intense what's going on here. So this is two-way communication between 2 totally separate processes now, right? The parent writes into write pipe 0, the parent writes into write pipe 1, the child can read the corresponding information from write pipe 0. That's how I got the X. And the child can write into read pipe 1, and the parent can read from read pipe 0 and see what the child sent. And it's extremely low level in the sense that, you know, I had to tell it to read 4 bytes. And what I read was just HA. There was no null terminator at the end. If I tried to print buffer as a %S, we might get lucky, but we'll probably get gibberish or a seg fault. Yeah, we got lucky. But there's no guarantee that buffer that we get back is going to have a null terminator on the end, right? In fact, it probably won't. But it's a way to send information back and forth. So a lot of programming at this level is about sort of finding the particular piece of machinery that lets you do something, and then using that piece of machinery is just programming, right? Now that just programming can be, you know, 6 months of your life, but if you know how to send information between 2 processes, right, then you can build a lot of different things on top of that. So if I wanted to be able to I don't know, have one process that's what's a good client server setup? I don't know, have a process that's going out and gathering information from the web, right? And I want a C program that can use that process to make queries and get information in some controlled way, pull down news stories from Reuters or whatever, right? If I can send an X from one process to another, or I can send haha from the second process to the first, right? I can build on top of that. I can use this structure to do very general communication. So there's still one thing missing here. Well, there's a few things missing. The big thing that's missing here is I wrote, the parent basically wrote out an X, and the child read that X, and then the child wrote a message, and the parent read the message. Right? They're moving in lockstep. So parent sends, child reads. Child sends, parent reads. And then if I wanted to, I could have the parent send something else and the child reads. What this doesn't let me do is have the parent send messages and have the child send messages and have them each read messages whenever they come in and send messages whenever they want. This is what we would call maybe a half duplex communication. We need coordination between who's sending and who's receiving. Because if I'm sitting up here and I'm waiting to read a message and the parent never sends a message, this read's never going to come back. I'm never going to get to send the message that I want to send. So we really need more processes. The child process actually needs a pair of processes, one that's sending and one that's receiving. And the parent process needs a pair of processes, one that's sending and one that's receiving. Okay, so I'm not going to ask you any of these details on a 224 exam. Okay, I may ask you some multiple choice question related to forks or something like that. But I'm not holding you responsible for programming this stuff. And if you go WSU, you'll take a 360 course there that's all about system programming, and you'll deal with this and a lot more. But we'll keep developing this next week as we have time. And in 223, we'll talk about how to do some of these things in Java, and it's a lot more sort of easygoing in Java because we have classes that let us do things like this. But we'll play around with making multiple processes that communicate in full duplex and so on. So we'll visit this again, and you'll see it after Clark. But next week after presentations, we'll go ahead and we'll finish up this code and make it full duplex and have some fun with it. All right, so have a great break. I will see you next week.